Good evening. Let's try that again. Good evening. That's better. That's better. My name is Kiki Zasimopoulos, and as CIERA's Director of Operations, I'm pleased to welcome you to the 5th Annual Astronomy Night Out. It's wonderful to see so many of you here with us in person, and I know there's many more of you on our live stream. First, I would like to thank our amazing staff. They're in the purple shirts. I think they're outside, so hopefully they can hear me. Our amazing staff, numerous volunteers. This event would not be possible without all of their hard work. I'd also like to extend a warm welcome to members of CIERA's Philanthropic Board of Visitors and other CIERA supporters who are joining us this evening. For those of you who are not familiar with CIERA, we're a Northwestern-wide research center focused on advancing astrophysics research with a special emphasis on connecting to other disciplines. So our exploration, our people, our impact extends to areas such as AI and engineering, the sciences, education, and the arts. And tonight's event is part of our extensive outreach portfolio. So before we begin, I just have a few housekeeping items so I don't get in trouble. This event is being recorded. The lecture will be about an hour, and that will be followed by Q&A. You probably saw we have a number of tables outside. Those tables will be open after the lecture as well. And we have groups with us tonight, including the Chicago Astronomer, Code Your Dreams, the National Hellenic Museum, Northwestern Classics students, CIERA's very own astrophotographer, Imran Sultan, and CIERA's Gravity Table. So at the main CIERA table when you came in, I do want to highlight something special. We have a QR code for you to fill out a survey, and this will enter you for a chance to win CIERA's photo book. This is a collection of images of the cosmos from our community. Ooh, yes. Thank you, Gideon. So please be sure to fill out that survey before you leave. I also wanted to highlight that Dearborn Observatory doesn't open until 8:30, so that does give you plenty of time to explore the tables. Starting at 8:20, every 10 minutes after that, we'll have someone who will walk folks over to the Dearborn Observatory, and we will do that until about 9 p.m. The observatory is open until 10 p.m. And of course, if you know your way there, you're welcome to just meet us there. All right. I think those are all the logistics. Now I am pleased to welcome and introduce Dr. Nick Winters. Nick Winters is an assistant professor of classics at Northwestern University. He teaches courses on ancient astronomy and ancient medicine, and in his research, he focuses on ancient mathematics and science. And his work on ancient astronomy ranges from practical topics like the geometry of celestial models and the manufacture of sundials, to more imaginative areas like astronomy and Pythagorean mysticism. He received his PhD from Duke University and went on to be an NEH Fellow at the American School of Classical Studies in Athens. In addition to his affiliation with CIERA, Dr. Winters is affiliated with Science and Human Culture Program, the Kaplan Institute for the Humanities, the Gender and Sexuality Studies Program, and Slivka Residential Engineering College. He is also an editor of an undergraduate research journal in classics and has taught a course for the public on ancient board games through the Norris University Center. With that, let's please give Nick a very warm welcome.
Good evening. Can everybody hear me okay? All right. For my own logistics, okay, that's working, good. It's not projecting though. I'm going to be showing you a series of slides today. I am also going to be briefly demonstrating things with these instruments here. I know that y'all in the back will not be able to see them clearly, but I promise you don't have to see them to understand what I'm talking about. It'll all be up on the slides. And One of my wonderful students from my ancient astronomy class is at a table out back with more of all of these things that you can look at afterwards. We'll have these up there as well. All right, without further ado. Well, okay. If I could see anybody, I would ask for a show of hands who else likes maps. Oh, I can see a couple. All right, excellent. So what I'm going to talk to you about this evening is a tradition of mapping the stars, in particular, that started here in Europe, at least, with the Nebra disk. This is a Bronze Age star map made out of bronze and gold plate. It was found in Germany. Is my mic getting feedback? Is that okay? You're good, okay. So a tradition that spans from over here at the Nebra disk all the way to today. This is an app that I have on my phone that has a grid map of everything that we can see in the heavens, all the constellations, the horizon at the bottom, coordinates, and you can program it for any time. So I can set this to 500 BCE, I can set this for 5000 CE. This is an extremely powerful tool. The Nebra disk, not so much, but it's a beginning. And what I want to tell you the story of is how we got from there to here, at least in one corner of the world. That's this corner of the world, the one that I study. Particularly special about the astronomy from this part of the world. There was astronomy going on in the Bronze Age in the Americas, in New Zealand, in China, everywhere. Basically, people have always been astronomers. This is the tradition that I know about, so this is what we're going to talk about. In particular, most of the stuff that I'm going to show you is coming from right in this area. Because I'm a Hellenist, I work on Greece. All right. So here's my plan for the next 45 minutes. I'm going to start by talking a little bit about why anybody did this in the first place. What's in it for people to map the stars, aside from what you can see at a glance? Then I'm going to talk a little bit about how they made a start, what kinds of observations they made, and with what tools that allowed them to start gathering the information that would gradually become star maps. Then, orientation, there it is. I'm going to start talking about the first celestial globes, star maps that are not particularly portable, but that show all of the heavens, the whole sphere of the fixed stars. Finally, I'm going to talk about the astrolabe, which is an incredibly powerful tool. I'm going to tell you a little bit about how it works. It is essentially a portable star map that is universal for any latitude that you have a plate for. We'll say more about that in a bit. And then finally, I'm going to conclude with just reminding us why anyone might want to know about how these maps, how this technology came into existence. You know, aside from being kind of a nerd about it, which you all are because you showed up here. So let's start here. Why did anybody do this? Well, what time it was they got from the sky. So keeping time. It's not just things like how high is the sun in the sky and how close is it to setting. It's also where is the sun in the circle of the zodiac. That tells you what time of year it is. What stars are visible at sunrise and sunset, and where are they at sunrise and sunset? That also tells you what time of year it is, and it tells you what latitude you're at. That's keeping both track of long time, which is difficult to do. If you don't have computers or clocks or standardized timekeeping devices, keeping track of long time is non-trivial. They use the stars for that. It also tells them where they are on Earth, because where the sun rises and sets, how high it reaches in the sky, and again, what stars are visible, those things change depending on what latitude you're at on Earth. If anyone who's been to the southern hemisphere, you'll know you'll see stars that you've never seen before. Okay. Then, for ancient people in particular, being able to keep track of long time, being able to recognize recurring long patterns in the motion of the stars and the sun and moon, etc., that gives them something of a command over the future that is very comforting for people who don't have many opportunities to have control over the future. Okay, so things like knowing when the next full moon is going to happen, knowing when the next eclipse is going to happen, being confident that you can tell when fall is just around the corner based on what stars rise, what time is it for plowing, are the crops going to be good this year? All of those things you can predict based on astronomical phenomena. This was very important to them for that reason. And finally, comprehending the divine. And all I mean by that is that in the ancient world, there really was not a difference. So this is not just the ancient world. This was true down into the Renaissance. There was really not much of a difference between astronomy and astrology. And the motions of the stars, celestial phenomena, these things were also considered portents, indicators of divine will or displeasure, predictions of like the outcomes of battles or which king is going to succeed to the throne, things like that. So all of this is a large incentive for people in the ancient world to know what's going on up there. We have attestations of this from the very oldest books that we have from this part of the world. Here is a quotation from Hesiod's Works and Days. When the Pleiades and Hyades and strong Orion set, remember it is seasonable for sowing, and so the completed year passes beneath the earth. The Works and Days includes a star calendar for agriculture. You can tell what to do on your farm by what stars you can see in the sky. In order to do that, you have to be able to recognize the stars. The Mediterranean, especially, was a seafaring culture as well. And out on the ocean, there are no landmarks except what's up in the sky. So this is a longer quote from the Odyssey, and I'll take you down. Hey. Odysseus steered his craft, sleep never closing his eyes, forever scanning the stars, the Pleiades and the plowman late to set, and the great bear that mankind also calls the wagon. She wheels on her axis always fixed, watching the hunter, that's Orion, and she alone is denied a plunge in the ocean's baths. That's because Ursa Major, the great bear, never sets at the latitude where Odysseus is. She's circumpolar. She never goes under the horizon. Okay? He kept these stars hard to port as he cut across the sea. Okay, these are the two of the couple of oldest books in European literature. And they both show people who are already relying on the stars to get around in the world. Now, these observations are fairly rudimentary compared to things like this that we have up here. But you still have to be able to recognize where the Pleiades are. And you notice that Homer, the poet, gives a whole description of the great bear, saying, you know, she doesn't dip beneath the horizon. She is always fixed, wheeling on her axis, you know, and facing towards the hunter. All that is a kind of mapping. It's verbal mapping. It tells you when you look up in the sky, how are you going to recognize which one's the Great Bear? So this is a store of information. It's not just beautiful poetry. All right. At some point, we start moving from that to information. Now, there's a long story there, and I'm going to spare you some of the gory details of archaic Greek history because it's a lot of warfare and bloodshed and tyrannies and various things. But in the Greek world, and especially in the Ionian Sea, which is this eastern part, the Ionian coast of Anatolia, there arose a culture of people that were called physicists, and they were philosophers, scientists who did work observing the heavens. They drew on a lot on the cultures around them, Babylonia over in Mesopotamia, Babylonian culture, and then the Egyptian culture south in North Africa. They drew on a lot of work that was being done in those parts of the world, but they started to make what we would consider more scientific observations of the cosmos, models of the heavens, and maps, observations that count as maps. So this is what we're going to move to now. And I'm going to show you a quick video of how the stars move. If you watch them, if you go out into the night sky and just stare up at it all night, you will see this just much slower. Okay, there it is. So this is what we mean when we talk about stars setting. You're looking west, and they're all sort of falling around you. Now those are the star tracks. Some great photography in this video. All right? So as you can see here, it's not just that the sun moves through the sky. The entire cosmos spins fully around the Earth every single day, including all of the stars. You might also note that there's a fixed point right there. That's the North Star, Polaris. So, the people who watched the stars and made these observations, they realized a couple of things. First, that the stars circle the Earth every single day. Second, that only some of them are visible at every time of year. That's because the sun moves backwards across the sky very slowly over the course of the year. One other thing that they observed that's very important is that all of the stars, except for a few of them that they called wanderers, planets, stay in the same relation to each other. They were called the fixed stars. And they were called the fixed stars because they only ever stayed still relative to each other. So it's like a big globe, like this, that just turns around the Earth once every day. That is the preliminary information you need to know to start mapping them. Before you can generate a map, however, you need data. You need to know what stars are up there and where they are relative to each other. For that, Greek astronomers borrowed a tool from architects and land surveyors. This is called a dioptra. Now, the original purpose of a dioptra is to measure elevation, okay, relative elevation. There's a sighting tube here that you can look through, right? And a plumb line would hang from that central peg. You can see this one on mine. Right? And this scale of degrees, 90 degrees, at the bottom of the quadrant, you can just read from the plumb line exactly what elevation you're looking at as you look through the sighting tube. Does that make sense? So, originally, this was for things like laying roads or building foundations. You want to make sure that everything is level, everything is lined up. Okay? The astronomers used it to measure what was in the night sky. If they could identify a single star relative to other stars, they could say, all right, this star was so high above the horizon at this point around the horizon, okay, on this date. And once you have that kind of information, you can start making lists of data, which is very exciting for me, and that eventually becomes a map. So a very fancy astronomical dioptra, well, it can be used by land surveyors too. It was, the design was improved by a Roman engineer, was Greek and Egyptian living in the Roman Empire. That happened a lot those days. Hieron of Alexandria, he designed a dioptra that had toothed gears that you could adjust so that you could fine-tune the dioptra and you could take measurements that were precise to within a degree of angle. And this became a very powerful observational tool for astronomers. You can see how it could be easily developed from this. But the ability to turn it azimuthally on that bottom circle, that is really critical. Because the dioptra works like this. Now, for people who are not such big fans of math, I absolutely promise this is the only math I'm going to show you. The only numbers, okay? For people who are big fans of math, come and see me afterwards. I've got a lot more like this. Okay. All right, so to use a dioptra, you imagine that you, the observer, are standing here in the middle of a wide open field, horizon all around you. That's this flat circle. Okay, that's the horizon. There's you in the center. Okay? You want to know where that star is. You've recognized that particular star. You've given it a name. You can tell where it is relative to other stars that are better established, other constellations, and so forth. So you start your dioptra at north. That's the 0 point for azimuth. And you turn that lower circle until it's at the point at the horizon where you just need to go straight up to get to the star. Then you shift the elevation of your dioptra until you're looking directly at the star you want to identify. And all you have to do is then read off your degrees from the bottom circle and from the quadrant, or the semicircle. Is this clear to everybody? Anybody want me to say it again? All right. All right, so this is a great system. It will allow you in a certain place to get observations on the movements of every star in the sky during the entire year. And that allows you to produce something like this. These are the earliest data tables that we have from the ancient world. They're called in Greek parapegmata. And all that means is a block of something that you stick pegs into, literally, the parapegmata. You can see the little holes here in this one, and there in the Mulapin tablet. This is from Babylonia, much earlier than the Greek example. But the Mesopotamians, you know, they were doing this long before any of the rest of us. So what these are is lists of stars when they rise and set, when the sun moves into certain constellations of the zodiac, and you can move the peg to different holes throughout the year to keep track of what stars are rising or setting. This is very helpful in case you have, say, overcast days, or you're a busy person in the city and you don't have time to stand outside looking at the stars at all hours of the night. Okay? So this is a great compendium of information. The problem is, it only works in one place. That type of observation that you can get from the dioptra, it'll tell you about your place on the Earth, your latitude, but it won't necessarily tell you about everything. And the Greeks, they weren't alone in this, but they definitely wanted to know everything. That's just kind of who they were as a culture. And they knew, one of the things that they knew is that the Earth was round, and it was in the center of the universe, and the edge of the universe was the sphere of the fixed stars that circled around it once every day. So this is the universe to most ancient people. Now, there were a couple of people who believed in other types of universes, including some heliocentrists in the ancient world, and some flat earthers in the ancient world. But for the most part, everybody who was doing astronomy in those days understood that the Earth was round and the universe looked something like this. Right? So if you really want a map of the heavens, you need a kind of map that will show not just what you'll see from your specific place on Earth, okay, but what anyone could measure from anywhere on Earth. Okay? You want universal coordinates. That's the next piece of making a map. It's a coordinate system that everyone can agree on. Okay? So first you need data, then you need standard coordinates. And that's what they came up with. They came up with a map of the globe, the celestial globe, that is, the sphere of the fixed stars, that they could kind of project a grid onto, and they could measure the position of every star in coordinates from the Earth at the center, as though it were just a point. Astronomers took that information and they put it into these massive data tables. These are some excerpts from the Almagest or Syntaxis of Ptolemy, Claudius Ptolemy, the great 2nd century CE astronomer. Almagest is the Arabic word for his book. It means the greatest book. And this was the book on astronomy until Copernicus rewrote everything. Okay. So what these are, right, are tables of the coordinates of different stars. Just pages and pages of them, meticulously, in fine, degrees, minutes, and seconds. It's extremely precise. And Ptolemy, in order to compile these tables, he drew on 800 years worth of data that had been compiled by Babylonian astronomers and Greek astronomers and Egyptian astronomers. He was extremely thorough. And once you have this, you have almost everything that you need to start producing actual physical maps. There's one more thing you need, and that is a frame. So, we're going to move now. How am I doing on time? We're going to move now to circles and spheres. I'm going to go a little bit quicker through this section. So once Ptolemy has all that data and all of those coordinates, you need a good way to portray it on the surface of a sphere to start with, okay? But on the surface of any map in such a way that you can find what you're looking for relative to some absolute landmarks, let's say. So what people did was they projected these landmarks, these spatial landmarks, from the Earth. So the equator of the Earth gets just projected straight out and becomes the equator of the celestial sphere. Then you have a very important set of stars here. This is the zodiac belt, or the ecliptic circle. The zodiac belt, there's nothing particularly special about it in and of itself. It just happens to be the path that the sun travels in throughout the year. these are constellations that absolutely everybody knows in the ancient world. Right? And the zodiac belt touches, the path of the sun turns, so these are called tropics because it turns there. That's what the word means. Here at the Tropic of Cancer, and down here at the Tropic of Capricorn. So that gives you 3 parallel circles towards the center of the celestial sphere, okay, that can act as reference points. Then you have the poles. You remember that still star, Polaris, when we were looking toward the north sky. And everything in the universe sort of spins around that one axis. Well, that's a fixed point. You can use that. There's Polaris. That's the Antarctic pole. Okay? And then the polar circles can also act as landmarks. The meridians are chosen because they are the points at which the ecliptic circle either touches the tropics or crosses the equator. Okay? Once you have all of those things, you have everything you need to put a grid over these coordinates and create yourself a map. So the armillary sphere is essentially a bare bones map of the heavens. It gives you those landmarks and the zodiac belt. Okay, there's that zodiac belt, the Earth in the center there. That's the Tropic of Cancer, the equator, the Tropic of Capricorn, right? The meridians. The thing that's cool about the armillary sphere is that you can adjust it. So the whole universe can pop right out of there, okay? And you can change the angle of it to be set for whatever latitude you're at. So then, this flat circle here acts as your horizon, and you can see on the armillary sphere everything that'll be above the horizon, everything that'll be below the horizon at any given time. You can even have a little sun that sticks on the ecliptic circle on the zodiac belt, and you can move it around the zodiac belt as it moves through those constellations. So this is not just a map. It's also a calendar. It's an observational tool. It'll predict, where on the horizon the sun will rise and set, how high in the sky it'll be at noon, and so on. Right? It's a powerful tool. It's also a map, but it only shows a few of it shows the sort of skeleton of the cosmos. It is a wonderful thing. They get more complicated. This one is in the Museo Galileo in Florence, and it's incredible. It's like twice as tall as I am, or 3 times or something. And it has all the planets. All those are moving parts. They all work. Highly recommend going to see it. I also highly recommend going to the Adler Planetarium, where they have a couple of different ones that you can play with in the basement. Okay? And if you're really into this, there is actually, I'm always plugging for this app. I think it's great. You can learn how to use an armillary sphere. I've put the download links there, and hopefully we'll be able to make these available to people if you want. At any rate, if what you want is a full map of the stars, you need to take it off the skeleton and put it on a whole globe. And ancient people definitely did this, but they still always used those same reference point lines. There's the Tropic of Cancer, the equator, Tropic of Capricorn. There's the zodiac circle and the meridians. You see that? Here's the zodiac circle, equator, meridians, Tropic of Cancer. And then the pictures drawn on there are constellations, which is a much older way of mapping the heavens, an easier one in some ways, less scientific, but very useful for people. Right? And they made tons of these. This is a beautiful one. It's a Roman copy of a Greek original. Atlas is the Titan who has to carry the entire sky on his shoulders. So I just love this depiction of him because they have the sky as a globe, which is great. And sure enough, there is the meridian, Tropic of Cancer, equator, Tropic of Capricorn, and the ecliptic circle, zodiac belt. Right? It's on all of these. Archimedes in the 3rd century BCE was famous for making one of these. This is a replica. It's not the one he made. But there are stories that he had moving parts attached to it that would show how all the planets moved around the heavens during the course of the year. Now these are maps. That's this. You have a celestial sphere, a grid over it, all of the stars are on coordinates. Anything that you want to know where to find, all you have to do is look and find it. These continue to be made for centuries and centuries, and you can still get them in some places. I've got one right there. But they are not particularly portable. They're still not what exactly we would think of as a map. A map is something you can fold up and take with you, right? And it's useful. It might be stackable and storable in a way that's slightly easier than that, believe me. So this brings me to the last part of this, which is probably the coolest device that I get to teach anybody about, the astrolabe. This thing is not just a map, although it is that. It is also a portable computer. It leaves the armillary sphere in the dust in terms of what it's capable of doing. It includes a star chart that is mobile, and you can move the stars around to different positions during the day or during the year. It includes everything that an armillary sphere can do with the sun and the zodiac belt. It includes calculations of calendars and clocks, not only daily time, but long time, okay? And conversion table, like a slide rule. Do you guys know what I know some of you in the audience know what a slide rule is. Okay, the astrolabe has that too. It is also an instrument of observation. It has on the back of it a little arm like this with a sighting tube, or sighting vanes, as in this case, that you can turn to get the altitude of a star, just like a dioptra. So it includes a dioptra as well. And finally, it is actually a calculator. Okay? So it will visually do calculations for you. Right? When I say that this is a map, that is an egregious understatement. This thing is a masterwork of projection geometry. Okay? And remember, this all had to be done by hand and with those endless data tables that you saw from Ptolemy. Okay? So inside the astrolabe, there are interchangeable plates that you can switch out that will map the celestial grid onto a two-dimensional disk for any latitude that you're at. They make multiple latitude plates. I've got a bunch of them here that I can show you, afterwards. The grid lines will be different for every latitude, but you've got a horizon here, meridian, okay? That's the Tropic of Cancer, the celestial equator, the outer circle is the Tropic of Capricorn, okay? That's the zenith, that's the point right over your head. That's the North Star, okay? So that projects that entire celestial grid that they took all that time creating, projects it onto a little tiny disk, etched out, that is ordered to your latitude specifically. And then on top of that, it puts another 2D projection of all of the most prominent stars in the heavens. So you see how on the astrolabe, it has this beautiful sort of netting over it that's called a reedy, a net. And what that is a map of the stars. So every little point there is a star. And the names of the stars are etched in the bars near to the little points. So that's why it looks like that. And the star will move along the coordinate lines etched into the latitude plate as you go through the day and through the year. The ecliptic circle is this circle on the reedy right there. See that? So that's the zodiac belt. And that will show you not only where the constellations of the zodiac are during the day, but also where the sun is, so you can tell when the sun is going to rise and set. All right. So these are two different projections, because they have to be. This one always stays the same. This one changes for whatever latitude you're at. And they have to all be perfectly coordinated in order for the astrolabe to work. And it does. And this thing used to be everywhere. Everyone who was a little bit fancy and maybe had slightly intellectual pretensions or something like that had one of these things. We have a bunch of treatises on them from the ancient world, and I have one at my students' table out in the back, written by Geoffrey Chaucer, the author of the Canterbury Tales. He had an astrolabe made for his son and wrote a little treatise on how to use it for him, right? So it's really cool. We've got dozens and dozens of these things, mostly from the Middle Ages and Renaissance. The Adler Planetarium has a stunning collection. I strongly urge you to go see them. And I've got a beautiful one here made by a very talented artisan in California that you're welcome to check out afterwards. So the thing is, not only is the astrolabe itself a map, and a portable one, and a storable one, but it is a tool. It's an instrument for generating more maps, because using the dioptra that it has on the back, you can go out anywhere you are and take observations of stars and make fine adjustments to the projection of your horizon plate, your latitude plate, and catalog new stars in the heavens or new celestial phenomena. It's incredibly powerful. And it's a work of art. I mean, just the craftsmanship on these things is stunning. All right. So I'm going to wrap it up here. We'll leave you with some thoughts about why we might study this aside from just really enjoying ancient star maps. This is a picture from the Cosmos Webb collaboration that's working with the James Webb Telescope. It is a tiny fraction of the night sky that we are now able to see. And frankly, that's dizzying. But I think it's difficult to even fully appreciate if you don't understand that we started here. And this is a star map, by the way. The Nebra disk, these are the Pleiades, right there. Okay? Gemini is behind the sun, there. So this is an actual map of the constellations. All of the work that it took to get to this point, where we can do this and we can do that, is really staggering. And understanding not just the sort of geniuses who came up with the clever ideas, but all of the labor that went into it. All of those scribes meticulously copying all of those numbers. All of those mechanical carvers and metal workers and stone workers who made these things and made them precisely and made them beautiful, not because they had to, but just because. That is all part of the legacy that produces these kinds of images. And I think that it's a rich history worth appreciating. So I'm going to leave it there. Yeah, we've got about 10 minutes for questions. Does that sound good? Thank you so much for coming. This has been a blast.
So we have 2 mic runners. If anybody has questions, they will bring the mic to you, and then you're welcome to ask your question. I should stand over here.
Hello. So
Hi.
I have a curious historical question.
Sure.
So you have been showing that these globes were made in like 2nd century CE, right?
Mm-hmm.
I was just confused why, not sure, how did they know about the Tropic of Cancer or like Capricorn? Because one of them is only in the one hemisphere.
Oh, ancient seafarers got a lot farther than is often believed.
Okay.
There are some historians who think that a few of them may have actually gotten across to the Americas. They certainly got to England in the north, to the Cape of Good Hope in the south, to Greenland. So
yeah, I was just curious about his.
yeah, they were surprisingly well traveled, yes, and they did see the southern stars.
Thank you.
I see a hand back here. Yep.
Kind of related, when did they calculate the size of the Earth? Because I'm seeing the models that you showed, and I'm sure that affects the math a lot.
There are many different calculations of the size of the Earth. People had been making attempts at it for, well, I want to say maybe 100 years or so before we get Eratosthenes' very famous one. If you've ever seen the Cosmos episode on that, you know Eratosthenes measured the Earth very famously using the shadows of 2 obelisks, gnomons, that he set up at different latitudes. He measured the difference between the shadows, and knowing the distance between them and the difference between the lengths of the shadows, he calculated the curvature of the Earth. The problem with that is that we do not know how long his unit of distance was. Because in the ancient world, unfortunately for us, if someone said that this is a 5,000 stades, that could be any number of distances. A stade was not a standard unit of distance. So it's possible that Eratosthenes was correct to within 1% error. It's possible that he was off by as much as 20%. So it's hard for us to tell exactly. But most of the ancient treatises that we have say that in comparison to the fixed stars, the Earth should be understood as a point. That it has the relationship to a point, as a point. So the way it appears in this globe, for example, or in the armillary spheres, that is purely decorative, and it's not meant to be to scale. Yeah, good question.
Is the position of the constellations and the orbits of the stars in the celestial globe today the same like thousands of years ago, or have they moved?
They have moved because of a phenomenon called precession, which is really, well, okay, they haven't, wait. Both things are true, actually. They have moved because the universe is expanding. The Greeks didn't know that. They have also moved because of precession, which is actually a shift in the orientation of the Earth's axis and poles. So which stars we see where has in fact shifted from ancient times. For example, the equinox used to be at the beginning of the constellation of Aries. The spring equinox used to be at the beginning of the constellation of Aries. It now falls in the constellation of Pisces. So things are not the same, but most modern star maps will take account of precession, and it was something that ancient people noticed. You know, people like Ptolemy, who had 800 years worth of data, they were able to notice the phenomenon of stellar precession, and all throughout the Middle Ages, people were trying to come to grips with it and figure out what it meant. Got one down here.
So how would like politics or like religion affect how like ancient people would like gather the information?
That is a great question. Sorry. I got very excited because that's an excellent question. There is enough to say about this that I could do an entire other lecture on it. But it depends on the time and place, first of all. In some places, like Alexandria, you had state-funded research institutions, most famously the Library of Alexandria and the museum, where they specifically paid astronomers to do this work and take observations. They also, royal courts in Babylonia, in many of the early Greek city-states, they would pay for astronomers to keep observations and advise the king about what the heavens were telling them and things like that. So there was a lot of money spent by people with power to control this information. There was also, in Greece at least, there was a growing culture of just publishing information and sharing knowledge around, and teaching schools started to crop up in many of the democratic city-states, and those were funded differently. You'll notice I talk a lot about funding. Politics and money are always connected, not just in the ancient world. And so the questions of who wanted to know what was going on in the heavens and why, that has a lot to do with who did that work. So the kings want to know because they want to know the will of the gods. Merchants want to know because they have to navigate, they have to get their goods places. Farmers want to know because they want a good harvest. They want to know when to plow and harvest and so forth. So most people, the good news is that most people had some interest in keeping astronomical knowledge current and accurate. So yeah, they found ways to get the work done. Great question.
So all of the models you showed us today don't account for like depth or a radius of a sphere. How did that come into play and change models?
How did it come into play in what?
Like, how did models develop after people realized that stars were different distances away from us, rather than on the surface of a sphere?
Right. So some of them didn't. Maps like this globe is current. Okay? And the reason that this stays the same and that the scale of the Earth and the heavens doesn't really matter is that this globe actually just shows what we can see in the sky. And the thing that's kind of cool about ancient astronomy is that for a lot of it, the stuff that we know as moderns doesn't actually matter. Like in terms of what we can see up there, it really doesn't matter whether the Earth is at the center or the sun is at the center or there is no center. Right? What we can see stays the same. And this is partly why it was so hard to get people on board with heliocentricity, because Ptolemy's model was accurate. You know. However, models now are less likely to be spherical globes and more likely to be things like this, that you can kind of zoom in. On this star chart app that I have on my phone, you can click on a star or a celestial body and it will zoom in all the way through space to get you there. Okay, so that kind of digital 3D model is probably the most significant change that's been made in that regard. Yeah. Good question.
We've got one in the back and then another one up front.
Hi. So based on the records that we have, do we have like a time frame kind of in terms of years, decades, centuries it took to get between the different tools that you have like on display and you've discussed?
Yeah. That is very difficult to say because these things don't necessarily leave the biggest impact in the archaeological record or the textual record. Once they're everywhere, we know they're everywhere. You know, like in late antiquity, by the time we get to late antiquity, 600 CE or so, astrolabes are all over the place. And we know that they're all over the place because there are a bunch of books about them. By the time we get to the Middle Ages, we have a bunch of them that have survived. But before that, we only have hints, and we sort of have to do historical reconstructions. We can do a little bit with the chronology of developing these types of instruments because there are certain things that you have to be able to know before you can produce an astrolabe, right? So, like, you have to have a certain level of understanding of projection geometry, for example. The problem is they had that already in the 3rd century BCE. Euclid wrote a treatise on it. Likewise, the dioptra, that thing is so old. I mean, a dioptra, in essence, is just a tube that you can look at. I have my students make one every year out of a toilet paper tube. So anyone could have that, and we wouldn't have it in the archaeological record. So it's very difficult to know exactly when any given technology came to be popular. If we're lucky, we have books on it. Like Ptolemy in the 2nd century CE writes about the armillary sphere, he writes about the astrolabe and so forth. So we do our best with that.
I saw a hand here first, if we can get the mic down to the front here, and then I see one over there next.
Hi.
Hello.
I am wondering how the ancients, or whether the ancients, were able to map more temporary phenomena in the sky, like recurring comets. Can you talk about that a little?
Yes, I don't know the answer to the comet thing. They certainly observed comets, but I actually don't know if they ever mapped them. However, we know that they did map certain temporary phenomena. Let me go back here. Yeah, there. Archimedes' globe, for example, mechanically shows the movement of the planets. That includes sun and moon. So it can map eclipses, for example. And another very famous ancient astronomical device, the Antikythera mechanism, which I don't have here, but come visit me in my office, I'll show it to you. That had a map that would show phases of the moon and eclipses in motion and things like that. The problem is temporary phenomena, especially something like a comet that only recurs every, say, Halley's Comet every, 75 years, isn't it? How do you actually map that if you can't tell the full trail of it? You can only tell that it's going to be visible for a certain time at a certain time. So, yeah, it's a little bit harder to put on a piece of paper.
What allowed the birth of the concept of a solar system?
Well, the solar system specifically was really only named that after we put the sun in the center and the planets all orbiting around it. So that's an artifact of heliocentrism that started in the 15th century or so. Well, I mean, as I said before, there were Greek heliocentrists, 3rd century BCE, but they didn't talk about a solar system. But in terms of a sort of map of the cosmos that includes all of the orbits of the planets and so forth around the Earth, the geocentric solar system, or geosystem, I guess, that was something they had already in the 6th century BCE in Greece. And they had versions of that in other cultures as well. I'm pretty sure Babylonia had one in the 7th century BCE, a map of that. Ptolemy's, which is the one that I know the best, has the Earth in the center, and then the orbit of the moon, and the orbit of the sun, and then Venus, or Mercury and Venus, and Mars and Jupiter and Saturn, the planets, and then the sphere of the fixed stars at the outset. So they did have an idea of those sort of nested circles or spheres. But that's an extremely old idea. But it only becomes the solar system, of course, after we put the sun in the center.
Time for one more, maybe? And then
Sure,
you'll be
yeah.
around later for additional questions after, yes, for a
Yeah.
little bit? Okay, so one more question here. I'm just going to take the first one that my mic runners give me. Okay, perfect. And then if you still have additional questions, Nick is happy to answer them later.
I am.
Did anyone notice a sudden change in a fixed star, like what we would know as a supernova or something equivalent in antiquity? And if so, what they attribute astrological impact to something like that as opposed to like a planet, which is familiar?
Yeah, this did happen. The example that's coming to my mind right now is that one of the Pleiades dimmed. And they came up with myths. This actually happened in several different cultures. There are myths about one of the seven sisters leaving the others behind, going away to get married in some cases, or dying in others, or something. But yeah, what they did was they mapped a myth onto that, because they already had the myth of the Pleiades as the seven sisters. That was one of those sort of global mythic topoi. And then the dimming of one of the stars out of view kind of led to a change in the story. But yeah, that happened also when people were taking scientific observations and, and keeping their tables and everything like that. But I don't remember, honestly, off the top of my head, if Ptolemy mentions that anywhere. I'd have to look back through. That's a great question. Yeah.
All right. Thank you again. Let's give Nick a warm applause.
Thank you for coming.
Thank you all so much for joining us. I do want to let you know that our next, our annual public lecture is the one we host in the fall. That will be October 8th at Kahn Auditorium. If you're on our mailing lists, you'll be receiving information about that. In about 10 minutes, we'll start walking people over to Dearborn if you're interested in going to the observatory. There are 2 flights of stairs, and it is not handicapped accessible, just to warn you about that. And then please interact with our tables outside, and we hope you have a wonderful evening. It's a lovely night, so we hope you enjoy. And don't forget to fill out the survey for that photo book raffle.
Okay. Yeah.